you want me to start? Hello? Are you there? Oni.
Uh, yes, he wanted you. Okay, just
All right.
3, 2, 1.
Access to reliable water transfer is a major challenge in rural, remote, and environmentally sensitive areas in the world. The traditional pumps are often expensive, energy intensive, harmful to the environment, or impractical. Our project, Water Stairs, aims to develop a device that is cost effective, easy to build, repair, and deploy, as well as environmentally sustainable.
We aim to build on our previous young scientists' work by improving overall system performance, while also pushing our design towards achieving record level capability. Today, we will present our design and the process behind it, including its development, how it works, and our key findings, before evaluating our results and outlining its real-world applications and future improvements.
Our current system was developed from our previous young scientist design, with the goal of improving key performance factors such as height, transfer distance, flow volume, and efficiency.
Our system is based on the principle of using air pressure and buoyancy to drive water movement, which allows water to be lifted without relying on traditional mechanical pumping. Our system also operates through a combination of buoyancy-driven lift and a pulse piston effect. As air pressure increases, bubbles form and carry water upwards. When pressure decreases, these bubbles burst at a critical point, pushing the remaining water further along the tube. This creates a cascading motion that enables continuous water transfer.
To refine our original design, we conducted extensive and repeated testing, involving experimenting with different design configurations, water types, tubing diameters, angles, and the number of stages within the system. Through this iterative process, we identified different patterns in performance and progressively optimized our design.
During the development stage, we built upon our original concept and explored multiple variations. This led to an unexpected but significant discovery, which allowed us to achieve a maximum vertical lift of 7 meters. Interestingly, this result came from simplified design with more efficient horizontal staging tanks, which far outperformed more complex configurations. Our discovery originated from a blank value, which prompted further investigation.
Through this process, we developed three final configurations: vertical, angled, and zigzag, each being suited to different environmental conditions and water transfer needs.
The first key element of our design is our pneumatic drive. This is the driving force of our design and generates the thrust required to make the water climb upward through the various climb stages. As shown in this diagram on screen, air is fed into the mixer tube from the solar air pump on the bottom left. Here, the air combines with the water in the tube and starts pushing both bubbles and water into the next stage, the drive loop. In the drive loop, the air flows through the top and the water through the bottom. When the pressure builds up in the top of the loop, it forces the bubbles out of the drive loop via the output on the right-hand side, dragging water with it. As water and air bubbles move from the 13mm tubing into the 6mm outlet tubing, the air and water are recompressed from this size difference, and the pressure pushing them forward forms them into combined bubbles and water slugs. As they move up the tube, they grow bigger, carrying water upward into the system.
The second key element of our design is the buoyancy and pulse flow, as can be seen in the animation I'm showing you and the model beside me. As the water slug rises with the water in front and behind the bubble burst at a critical point. Some of the water droplets that were being carried exploded upwards into the staging tank. The remaining water slug droplets slowed down by the friction and the curvature of the tubing until the next water slug collects these droplets and continues the process.
Finally, the last key element of our design is our staging tanks. The staging tanks are situated at the top of each climb stage and perform two functions. One, relieving the back pressure, which could make the system stall, and two, recombining the air and water to then push it up the next climb stage. As illustrated in the diagram, the air and water slugs from the previous climb stage enter from the left side of the staging tank, and the expansion from 6mm to 13mm allows them to decompress and separate, where they recompress into water slugs and pressure from behind them pushes them forward up to the next staging tank.
This all distinguishes our system from conventional pumps, as unlike our design, conventional air pumps require high energy input, as well as continuous mechanical motion. Conventional pumps work by using high volumes of compressed air to generate loads of bubbles to drag the water up. The bubbles only have a limited distance above the water level before they pop and release the dragged water, limiting the height they can raise water to 1.5 meters, compared to our 7+ meter system. Additionally, they are also expensive, difficult to maintain, and not energy efficient or quiet, This in comparison to our design, which is cheap and simple to run and operate and can run off a solar panel.
Our system achieved a maximum lift of 7 meters, with flow rates between 0.06 and 0.082 liters per minute. Note that in our report, we accidentally stated the flow rates as 0.6 and 0.02 liters per minute. Our design only required 2.5 watts of energy, which is compared to approximately 16.3 watts for a mechanical pump, although we had lower flow rates. The efficiency of our system was highest with salt water, then dirty water, and then tap water.
Through testing, we identified several key variables that significantly influence performance. The tube diameter and length were critical in determining flow rates. 13mm diameter tubes reduced resistance significantly, but made bubble formation less effective. 6mm tubing provided to be the best balance between the two factors. Shorter distances between stages additionally resulted in higher flow rates.
Climb angle also had a major impact. Steeper angles cause back pressure and stalling, while an angle of around 20% provided the best balance between lift and flow. Air pressure affected both height and stability, but lower pressure improved bubble water cohesion. However, it did reduce lift, but higher pressure did increase height but could disrupt water movement if excessive.
Tube coiling also influenced resistance. Fewer coils increased the flow rate, while more coils reduced backflow but added resistance. In vertical systems, however, additional coils help counter gravity. In terms of configuration, the vertical system achieved the greatest height, the angled system produced the highest flow rates, and the zigzag system was most effective for shorter lifts.
Key advantages of our design include low costs, simple construction, minimal maintenance, no fuel requirements, and the ability to operate off-grid, including with contaminated or corrosive fluids.
However, limitations include lower flow rates than conventional pumps, sensitivity to setup, scaling challenges, and potential sediment buildup over time.
Our system has strong potential for rural and remote environments, being used for livestock, irrigation, watering of crops and plants, and transferring water or other liquids into storage tanks. As determined from our testing, our system can move different liquids whilst also having the potential in lakes, rivers, fish ponds, swimming pools, dams in the wild, etc., but may struggle at beaches or shallow steps.
We received much support from our parents, particularly with testing, discussions, and some construction processes. Ryley's younger brother Flynn was initially a member of the project, but due to age requirements, he could not be a part of this competition.
AI tools were used to support our understanding, visuals, and research, but they were not used for design ideas.
In conclusion, we improved the water-state system's performance in height, volume, and distance, creating a low-cost, low-energy, and environmentally friendly water transfer option. While its flow rate is lower than a mechanical pump, it can run continuously with minimal power. Future improvements will focus on better materials, high flow rates, and greater lift height.
Thank you.